talking to me? Oh, yeah, sorry. My name is Charlie and I'll be your host for this DVD. A key factor in audio engineering is having the right mentality, what is often referred to as having a vision. For example, most professional audio engineers have a clear idea what the finished material will sound like right from the beginning. What this DVD aims is help develop a general understanding of studio equipment, connections, as well as recording, mixing and mastering techniques that can take years of experience to develop. Most audio production techniques are rather arguable, although there are elements and key areas that, if handled the right way, can immediately raise the overall quality of your productions. The rapid advancements in technology constantly change the equipment used in modern studios, although the principles of audio production, such as capture, manipulation and reproduction, remain the same. Modern studio consoles, digital audio workstations and audio plugins often mimic the design and sound of the original equipment. Therefore, becoming familiar with the functions, controls and connections of the traditional studio can help understanding and being able to use past, present and future studios with ease and success. So let us get a glimpse of the following DVD chapters. Traditional studios consist of two essential rooms. The main studio, which is often referred to as the live or recording room, and the control room, where monitoring and mixing takes place. Optional rooms can be found in high-end professional studios such as the machine room, drum booth, and vocal booths. Machine rooms are often small isolated rooms used to install noisy equipment such as desktop computers and hard disks, effectively reducing unwanted noise from the control room. A drum booth is very similar to recording rooms, although it can be specifically acoustically treated and designed for percussive instruments. Vocal booths are often found in post-production studios, where they are used for producing voiceovers. So let's take a closer look at the equipment that can be found in a recording room. One of the first things that comes in mind when we hear of a recording studio is microphones. Microphones is where everything begins. Their role is to capture and convert acoustic sound, which travels through air, into electrical signals which can then be processed, recorded, and reproduced. Most microphones require a device called mic preamp in order to function properly. This is essential due to microphones' low output voltage. The role of a mic preamp is to raise low output voltage into a stronger, more usable signal. Professional microphones primarily use balanced cables with female and male XLR3 connectors. Due to their enormous importance in audio productions, microphones will be discussed in more depth in Chapter 4. Before moving forward, it would be a good opportunity to refer to one of the most important terms in audio equipment. It is called line level. Line level refers to the strength of an analog audio signal between audio components such as mixing consoles, reference monitors, and outboard effects. Signals must be amplified to line level, where they are more easily manipulated by other devices. This also helps signals arriving from different sources to provide a more ideal loudness, making the engineer's work easier. When looking at equipment manuals or at the back of a console, you might notice the following most common line level markings. The +4 dBu found in professional audio and the -10 dBV found in consumer audio. Learning to recognize these markings can avoid distortions or poor signal issues. The next piece of equipment is the stage box. Stage boxes are very common in live audio applications. Microphones and other devices are connected to a stage box in order for their output signals to be transferred in the control room. But how are the signals connected with the console which is situated in the next room? The answer is the snake. A snake is a multi-core cable which consists of several balance cables intended for carrying a big number of discrete electrical signals for multi-track recording. Often in professional studios, the snake is planted and carried throughout the walls during the construction stage. This is done to achieve isolation between the two rooms and, in short, to avoid cables going in and out of open doors. A snake often carries fallback signals for communication between the two rooms, as well as other useful connections. Headphones play a substantial role in the recording studio. In modern audio productions, parts of a song or a dubbing process is carried out on different occasions. In order for the performers to be in time, they have to be able to listen to the existing material without it being picked up by the sensitive microphones. This is achieved through headphones. Headphone preamps amplify the line level signals arriving from the snake to a level that can drive headphones. Another piece of equipment that we usually find in recording studios is DI or direct input boxes. To understand the main role of these devices, we have to mention that the end of the snake, which is situated in the control room, is broken into several XLR connectors, usually connected directly to the microphone inputs of the console. These inputs, of course, lead to the console's preamps. If a signal with a high output voltage is connected directly to a microphone preamp, there is a high possibility of distortion as well as causing irreversible damage to the preamps. Therefore, DI boxes, as their name implies, are used to directly connect high impedance or line level unbalanced signals arriving from instruments such as electric guitars or synthesizers to low impedance balanced microphone inputs. To make it even clearer, an electric guitar output would usually be transferred to a DI box through a 1/4-inch jack cable and then from the output of the box to the stage box to eventually reach the console's microphone inputs. Let us not forget that professional studios will also have a great range of cables, as well as solid microphone and music stands. We will be looking at studio connection systems, including inputs, outputs, cabling and transmission methods later in this chapter. Now let us take a closer look at equipment that can be found in a control room. After signals arrive in the mixing room, through the snake, every discrete signal is connected in the appropriate input or output in the back of our console. To make the whole process easier, snakes often come numerically labeled or color-coded in both ends to ensure that every signal goes into the correct connection. Here we are at the heart of every studio. This is of course the mixing desk, or console as it is often referred to. But what makes this piece of equipment so important and expensive? Well, the answer is a lot. So let's see some of the most important. Signal-to-noise ratio is a measure of signal strength relative to background noise, usually measured in dB. The higher the ratio, the less obtrusive the background noise is. A high-end studio console will provide a good signal-to-noise ratio. Every piece of cable or inner circuit of a console introduces a very small amount of unwanted noise to our original signal. Noise is always present in signals. Minor amounts of noise are not a problem since they are not that noticeable. On the contrary, great amounts of noise destroy the clarity and purity of our recordings and final mixes. If you are not familiar with noise, try the following. Stop playing back any sort of sound material and gradually raise the volume of a speaker amplifier. What you can hear is noise. Another reason that makes expensive consoles so important is their effect on our recordings, or as many refer to it, its sonic signature. Parts of a console that are responsible for this are microphone preamps, filters, summing channels, and many others. For example, many experienced audio engineers know that if the EQ section of a console is not bypassed during recording, it can have an apparent effect on our recordings, even if the gain dials are set to 0. This is due to the filter structure and analog nature of the console. This is also due to the signal passing through the electronic circuit that implements the EQ. One of the most important features that a good console can provide is flexibility. This has to do with how well a mixing desk has been designed. It mainly depends on the set of a console's connections, as well as all the available controls and sections. For example, a well-designed console provides enormous routing possibilities, as well as pre-post options for altering the order in which different sections and effects are applied, or for altering the functions of a slider. Moving back to equipment that can be found in control rooms, let us refer to patch bays. Patch bays are essential in studios. Imagine having to change the connections in the back of a console every time the need to use an outboard unit came up. Patch bays are typically rack-mounted panels which house cable connections. Patch bays are used to conveniently change the path of a selected signal. State-of-the-art studios also use digital patch bays, which do not require physical patching for rerouting signals. High-end preamps are also available as outboard units. Due to their great effect on recordings, manufacturers have made it possible to own professional preamps without having to purchase the original enormous and expensive legendary analog consoles. There are three types of preamps: transformer, transistor class A, and tube. Transistor preamps are the most common. If you are interested in preamps, but you do not know which ones you are after, it would be a good idea to pop in a music store and have a listen. Even easier, you can download from the internet acoustic material that is recorded through different preamps and compare the results. Although not a hardware piece of equipment, digital audio workstations, or DAWs in short, are probably the most essential part of every modern studio. During the digital revolution in audio production, DAWs replaced many expensive parts of analog equipment and made producing professional results possible even in low-budget project studios. At this point, DAWs offer recording, editing, and mixing capabilities to everyone. Although learning how to use this equipment the right way is now the difficult part. DAWs offer great sound quality, settings recall, as well as high track count and enormous flexibility. Digital converters are a very important part of every studio. In order for an analog audio signal to be recorded in our digital audio workstation, it has to be first converted into digital information. This process is what we call analog to digital conversion, or ADC. The reverse process, DAC, which stands for digital to analog conversion, has to be applied before we can hear back our recordings. Most people are not familiar with these devices since they are often part of our audio interfaces. In big studios, digital converters are used to convert big numbers of discrete channels for multi-track recording and reproduction. Some audio devices, such as outboard effects or digital audio tape machines, often provide digital inputs and outputs that allow them to interconnect via digital audio. Contrary to analog audio, digital signals and devices require to be synchronized with the word clock in order to function correctly and avoid data errors. We will be looking at some digital audio formats in the interconnection section. Monitors, or reference monitors, as they are often called, are one of the most important elements of a mixing room. The word reference arrives from the concept that what comes out of our speakers is a clear representation of the signal that arrives from the mixer. There are two main types of studio monitors: passive and active. Passive monitors require an additional speaker amplifier in order to output the adequate monitoring loudness. Active monitors can power up themselves. Active monitors are more often preferred since they are more compact and simply because they come with dedicated and specifically designed amplifiers. This simply saves the user from the quest of finding the appropriate amplifier.
We're sorry, the number you have dialed.
Another reason that makes active monitors preferable to passive monitors is the fact that if one of them has an unexpected failure, it can easily be replaced with another matched unit when time is of the essence. Matched active monitors can also be used to form other monitoring formats, such as 5.1 surround. A good set of studio monitors will provide a good frequency response and a pure undistorted sound. But why do professional studios have 2 or 3 sets of speakers? The answer is simple. It's called AB. Different speakers sound different. If we only use a specific set of speakers along all the production stages of a song, it might end up not sounding that great when reproduced on another set of speakers. This is what we refer to when we say that a mix does not travel well. As we will see in the following chapter, the acoustics of a room also play an enormous role in this. For this reason, audio engineers reference the material which they are working on by individually soloing the A or B set of speakers, trying to achieve a mix that will sound balanced and pleasing on all different sets. Not all monitor sets require subwoofers. To make this clear right from the beginning, subwoofers are not intended for boosting low frequencies, but for extending the low frequency of our monitoring system. Therefore, subwoofers have to be installed correctly to function well in conjunction with other speakers. The 2 most important settings to look for are gain and crossover frequency. The gain can be used for volume adjustment, while the crossover settings control the frequency under which signal will pass through. Having more than 1 subwoofers in a studio is better. Low frequencies below 80 Hz are not directional enough to localize. This technique helps developing a more even and balanced low frequency. Monitor placement is also very important and will be discussed in the acoustics and studio design chapter. Outboard units is another type of equipment we find in studios. They can be analog or digital effect units for audio signal processing, or other kind of equipment such as analog to digital converters and DSP accelerated units to run multiple plugin effects in real time without introducing any latency. In smaller studios, or more often project studios, we also see monitor controllers. As their name implies, they are used to easily control the monitoring level of our studio monitors. Bigger studios do not require such a device, since this functionality is provided by the mixing console. A monitor controller can easily be replaced by a small mixer. A relatively new piece of equipment that we find in modern studios is room correction devices. Some of them come as software plugins and only use a measurement microphone, while others come as hardware outboard units. What are they? Make sure to watch the next chapter. Modern studios also have powerful desktop computers modified for audio production. They are mainly used as hard disk digital recorders and to run the digital audio workstations. Some studios still have digital tape recorders due to their distinct sound and character. Widescreen LCD monitors are also something usual in modern studios, since they can be used for film post-production or just because they make the use of DOS more convenient. MIDI controllers are also common equipment in modern studios. MIDI controllers can be used to control DAWs and software plugins with greater ease, and in general to improve workflow. Synthesizers and samplers are also common in studios, although they are rapidly replaced by software plugins. One last piece of equipment that is not that often seen in studios is power conditioners. Power line conditioners, or stabilizers as they are often referred to, are used to reduce line noise by improving the quality of the power that is delivered to the electrical load equipment. These devices are important in high-end studios for ensuring smooth operation of the studio equipment and lower line noise. Analog audio connections are relatively easy to understand and use due to the fact that only cables and connectors are needed for successful transfer of signals. Before moving on, it is very important to understand the difference between a balanced and unbalanced connection. An unbalanced cable is made of two wires. One of them is the ground line, which is also referred to as common, earth, shield, or DC return. The other is the signal line, often referred to as the hot line. In order for a cable to be balanced, a third wire which carries the cold line is required. The hot and cold signals are identical, but 180 degrees out of phase. It is only when balanced cables are connected to differential or balanced inputs that a true balanced interconnection can be achieved. In short, differential inputs have the ability to reject hum and noise picked up equally by both the hot and cold leads. In general, when transferring signals over long distances, it is always better to use a true balanced cable since it helps reduce susceptibility to external noise. So let's try to familiarize with the most common analog connectors used in music studios. XLR, or more specific XLR3 connectors, are mainly used for professional audio. They are more often used for connecting microphones or line-level signals between digital converters and outboard units. XLR cables usually come with a female and male connector. XLR cables are balanced. TRS and TS connectors are more often referred to as audio jacks. There are two main types of these connectors: the TRS, which arrives from the words tip, ring, sleeve, and the TS, which is simply tip and sleeve. The quarter-inch TRS cable can either be used for unbalanced stereo interconnections or as a balanced mono cable. On the other hand, a quarter-inch TS cable is simply a mono unbalanced cable, often used for connecting electric guitars and other similar instruments. The RCA connector, often referred to as cinch connector. Although RCA connectors are primarily used in consumer audio, they are sometimes found in semi-professional audio equipment as alternative connections. RCA cables are unbalanced. Mic inputs are usually female XLR sockets which accept balanced low output signals arriving from microphones or DI boxes. Instrument inputs are unbalanced female quarter-inch TS sockets which accept high impedance or high Z signals arriving from electric guitars and similar instruments. Line inputs are line-level inputs which accept either balanced male XLR connectors, balanced TRS, or unbalanced TS quarter-inch jacks. Line-level inputs can either accept -10 or +4 dB signals. Another type of inputs are returns and accept quarter-inch TRS or TS connectors. Send and returns are usually balanced or unbalanced line-level connections. Direct outs and sends are often XLR balanced outputs on high-end professional consoles or TRS balanced outputs on smaller mixing desks. Direct outs, as their name implies, are used for multi-track recordings and output microphone and instrument line level signals after being amplified by preamps. Sends are used for adding outward effects into a signal chain. Both are line level connections. Monitor outputs are often XLR balanced, TRS or TS sockets outputting line-level signals for connecting reference monitors and monitor amplifiers. These sub-sockets and plugs are often used in professional studios for connecting great number of discrete analog signals to digital converters and audio interfaces. These subs carry line-level signals. So let us now take a closer look to the most common digital connections found in modern studios. SpeedIF can carry stereo channels and does not require an external word clock or synchronization since it is embedded in the signals. SpeedIF is more often used in consumer audio, but is sometimes found in professional audio equipment as well. SpeedIF can either use electrical coaxial cables with RCA jacks or optical fiber toslink cables as they are called. ADI stands for Alesys Digital Interface and is a more powerful digital audio transfer protocol since it can carry up to 8 tracks in a single fiber optic cable. These connections were first available on Alesys digital audio tape recorders. Synchronizing 2 or more of these devices is also possible for raising the overall number of channels. The ADAT Pipe protocol is now available in analog to digital converters as well as input cards for digital audio workstations. ASCBU or AS3 is another protocol for carrying digital audio signals. In professional audio interconnections, it uses either XLR cables or D-sub connections for carrying 16 channels of digital audio. MADI stands for Multi-Channel Audio Digital Interface and is a more advanced transfer protocol that can carry up to 64 channels of digital audio in high sample rates. What is very important to understand right from the beginning is that MIDI does not carry audio. MIDI stands for Musical Instrument Digital Interface. MIDI was designed for communicating, controlling, and synchronizing equipment such as electronic musical instruments and computers. MIDI was originally carried using DIN connectors, but is now also carried through USB cables. MIDI has a wide range of abilities but one of the most common is using a MIDI master keyboard for performing sounds available in plug-in instruments or controlling our DAW. MIDI sends messages such as pitch, velocity, and aftertouch for controlling other devices. MIDI carries an overall number of 16 channels. In audio engineering, signal flow refers to the path that an audio signal takes from source to output. For example, the signal flow chain in a traditional studio could be source, preamps and line level inputs, optional processing, AD converters, recorder, DA converters, post-processing, and monitors. As an audio engineer, it is very important to know the path that the signal takes at any given instance, as well as alternative routing options that can help improve signal-to-noise ratio by avoiding unnecessary connections. Now let us talk a little bit about acoustics. Why are acoustics so important in music production? Well, the answer is because we want our mixes to translate well when reproduced in other environments. For example, a great sounding mix on which we spent hours and hours perfecting might sound dull or too bright in another room. This is due to the impact of the room's acoustic quality on our mix. All medium or small sound reproduction rooms pose particular problems in acoustic design. Reflections from the hard surfaces of a room tend to cause imaging problems and color the sound, while low frequencies develop unwanted modal problems, in other words, standing waves. These issues are considered right from the beginning in high-end studio design. Although additional acoustic treatment is always essential for limiting such problems. There are two ways of limiting these problems, namely absorption and diffusion. To effectively use this, at least basic knowledge on the fundamentals of acoustics is required. What we have in this studio is the live-end, dead-end design concept. Other common concepts are the reflection-free zone or non-environment. As you can see, the front and side walls of the studio are covered with thick absorption panels, some of them angled. This helps limit low mid to high frequencies from bouncing, therefore distorting our stereo image and improve room mode problems. On the contrary, the back of the studio features custom diffusers which aim to evenly spread the arriving sound waves. As you can notice, the acoustic panels on the ceiling, along with the thick double windows, are angled, limiting room modes, while a broadband absorber is situated in the back of the left side wall. 3D diffusers are situated at the back side of the ceiling for further diffusion. In general, absorption panels are good for limiting medium to high frequencies when placed on the front hard surfaces of a studio. The absorption quality of a panel in low frequencies depends on its thickness. When extensive modal problems are apparent in a studio, broadband absorbers or bass traps are the answer. Angled surfaces and diffusers are always helpful for evenly spreading sound waves and limiting standing room modes. If you have an untreated room, Avoid placing monitors in the corners. Remember, corners always increase a monitor's efficiency in low frequencies. Use angled absorption panels in the side walls primarily at the point that the off-axis waves from monitors bounce directly back to your ears, when located in the sweet spot. Try avoiding to place monitors on your mixing desk's neck due to the early reflections developed from the desk's hard surfaces. Monitors are better placed on decoupling pads. Avoid placing monitors near corners. Place your monitors so that the tweeters are facing your ears, meaning that placement should be as much as possible for you and the two monitors to make the three corners of an equilateral triangle. Height is also important. Tweeters must be at head height. The closer the monitors from the monitoring position, a more accurate placement must be achieved. A few centimeters can make a difference. Room correction systems aim to improve the frequency response of a control room using equalization. Room correction has been applied for many years, although room correction systems aim to do most of the process automatically and more accurately. In short, room correction is based on measuring the frequency response of a room and then compensating dips and peaks using equalization. Most often, room correction systems will offer two options for monitoring: one for the sweet spot and one for the room as a whole. Room correction systems can limit the effect the frequency response of a room has on our mix. Let us not forget that acoustic problems are not only present in frequencies but in time domain as well. Thick absorbing panels cost a lot, especially when on a budget. If a gap of free space equal to the thickness of the panel is left when mounted on the wall, its absorbing quality can improve greatly. If built-in custom diffusers is simply out of question, a bookshelf filled with old books and placed in the back of the room can do the trick. If you can afford an acoustician, hire one. Electricity is very important in a studio. If a studio offers an unstable current, this can only have a negative impact on our equipment and productions. Good cabling and installation is also important, as well as grounding to eliminate unwanted hum and buzz from our signals. Even using the right lighting can be very important in a studio. Ideal working conditions is something that is often neglected in low-budget studio designs. For example, project studios often lack proper ventilation or air conditioning, which makes working for long hours impossible and simply causes the expensive equipment to overheat. Daylight comfort is also a very important aspect, since it has an enormous impact on our artistic side. Good isolation is very important, not only between the various rooms, but from the outside world as well. Sound isolation is often misinterpreted in acoustics. Sound isolation refers to sound not going in or out of a room, while acoustics refer to the way sound waves are reflected in a given space. Isolation is essential to make sure that sound does not pass from the recording room to the control room or vice versa, Otherwise, we will not be able to monitor or record properly. We also do not want mechanical sounds from the outside world to reach our studio. And finally, a professional studio must be able to work after hours, and that would definitely not make our neighbors happy. Every experienced audio engineer or producer knows that good raw recordings are the key to a successful mix. Mixing good recordings is fun, while mixing poor recordings is more or less a compromise. But how can we achieve better recordings? The answer is simple: microphones. Proper selection of microphones and microphone placement plays a substantial role in the overall sound of a song right from the beginning. So let's give a closer look at microphones. Without becoming too technical, based on their transducer principles, there are two main categories of microphones: dynamic and condenser. Other categories include the piezoelectric and fiber optic. Dynamic microphones use electromagnetic induction, whereas condensers use capacitors to convert acoustic to electric energy. Dynamic microphones are used more in live sound and condenser microphones in studios. This occurs due to their characteristics. Dynamic microphones are robust and can handle high-velocity pressure waves, or in other words, very loud sounds. For example, dynamic microphones can easily handle the output of a cranked-up electric guitar amplifier, whereas a condenser can be permanently destroyed. On the other hand, condensers cost more and are not as durable to moisture or extreme use. Throughout the years, microphone manufacturers are constantly improving the durability of condenser microphones, although the use of an expensive condenser microphone in the inside of a kick drum is not an option. So why ever use a condenser microphone then? Well, condensers are typically more sensitive to sound as well. For example, if we want to record an orchestra from a relatively long distance, condensers will easily achieve the required levels and detail. Condenser microphones require electricity or phantom power, as it is often referred to. All professional consoles and microphone preamps provide a phantom power switch for this exact reason. Always remember to switch it on after connecting a microphone and before disconnecting it, as well as if it's required in the first place. The smaller the diameter of the diaphragm, the better the high frequency response, and vice versa. Dynamic microphones are less responsive due to their great mass. Condenser microphones are in general better at capturing transients. Condensers are brighter. The second most important aspect to look for is the directional characteristics or polar pattern, as it is often referred to. Let us go through them once and try to familiarize with their qualities. Omnidirectional, as the name implies, are intended to pick up sound equally from all directions, although as you will soon notice, that is not the case, or at least according to frequency. Cardioid, on the other hand, pick up more direct sound on axis and reject off-axis sounds. Again, as with omnidirectional microphones, sound is not completely rejected when off-axis, but it's reduced in high frequencies. Supercardioid and hypercardioid are more extreme versions of the cardioid pattern. Bidirectional or figure of 8 picks up equally from the front and the back, while sound coming from the sides is rejected. Last, we have the shotgun pattern. Shotguns are highly directional microphones often used in film post-production due to their ability to pick up specific sound sources in detail and adequate levels when pointed at them. Place a matched stereo pair of cardioid microphones one over the other as seen in the video. The formed angle might range from 90 to 135 degrees. The bigger the angle, the wider the stereo image. Be careful, bigger angles can cause a gap in the middle of our stereo image. ORTF is similar to X and Y, although as you can see, the microphones are now spaced. This can achieve a wider stereo image, but is also more prone to developing phase problems when not used properly. This technique aims to mimic the human hearing. As shown in the video, in the spaced pair technique, there is far more space between the microphones. This technique is very common in drums recording, used for the overheads. If you intend to use this technique for recording a classical ensemble, it is important to consider the 3-to-1 rule. In short, the 3-to-1 rule says that the distance between the A and B microphone must be 3 times or greater than the distance of microphone A from the sound source, to avoid phase cancellation. To form the Blum-Lane pair, use two matched microphones with figure of 8 patterns, one over the other as demonstrated in the video. This technique can achieve a very realistic stereo picture since the ambience of a space is captured as well. Placing the microphones near to the instruments will result in capturing more of the direct sound, while placing the microphones further back will capture more of the room's ambience. Half a millennium ago, audio production was all about finding the right space, setting up a microphone, and capturing a good performance. Then came the analog signal processors and multi-track recorders, allowing audio engineers of the time to bring their productions to another level and sophistication. In modern productions, the use of audio signal processing is considered essential, and some sort of processing is even used in classical recordings. The tools used for signal processing are called effects. Effects come as analog and digital hardware equipment, as software plugins, or as plugins running on digital hardware equipment. Effects can be divided into 4 main categories: equalizers, VGA, which stands for variable gain amplification, delay, and reverb. Equalizers can shape the temp of an audio signal by amplifying or attenuating a signal at a given frequency. EQ effects consist of a series of filters. The main controls of an equalizer are gain, which controls the amount of boost or cut applied to the original signal, sensor frequency, which controls the frequency at which the gain is applied, and Q, which stands for bandwidth and controls the number of frequencies being affected around the center frequency. There are three kinds of equalizers based on the range of feature controls. Peaking or graphic equalizers provide a set of given fixed bandwidths at which the user can raise or lower the gain. Such equalizers are often used in live sound systems and semi-professional equipment due to their limited parameters. Semi-parametric equalizers have also the ability to control the sensor frequency at which the gain setting is applied. Parametric equalizers can control gain, sensor frequency, and bandwidth. While using EQs, you might come across some interesting terms. To point you in the right direction, here is a short list of the most important. Cutoff frequency is the frequency at which a high or low frequency EQ section starts to take effect. Slope is the rate at which a high or low frequency EQ section reduces the level above or below the cutoff frequency, usually 6, 12, 18 or 24 dB per octave. A high-pass filter cuts low frequencies, while a low-pass filter takes away high frequencies. A bandpass filter passes all spectral components of a signal in between a set frequency range. A notch filter is a filter that cuts out a very narrow range of frequencies. Shelf EQ is an equalizer where the change of gain applied above or below the cutoff frequency extends to all the subsequent available high or low frequencies. Channel EQs tend to color the sound of our recordings, while other equalizers can be designed to be more transparent, in other words, not imposing a sonic signature. In equalizer plugins, there are two main types of digital filtering algorithms. The IIR, which stands for Infinite Impulse Response, and the FIR, which stands for Finite Impulse Response. Linear phase EQs, for example, use FIR algorithms and tend to be more transparent, which is one of the main reasons they are often used in mastering. There are many types of effects in this category, but we will focus on the most important: noise gates and compressors. Other effects include limiters and expanders. In short, a noise gate allows a signal to pass through when it reaches a certain amplitude, and vice versa. The point at which this occurs is called threshold and is measured in dB. A noise gate can completely cut the signal when it falls under the threshold, or simply be attenuated by a certain amount of dB. This is controlled by the reduction or attenuation setting. Other controls found in a noise gate are the attack and release, and are measured in milliseconds or seconds in more extreme cases. The attack controls how fast the signal reaches full amplitude after reaching the threshold, while the release is the time it takes the signal to decrease when the original signal falls under the threshold. A final common control is the hold setting that determines how long the signal will remain in full amplitude after the attack. Keep in mind that if the attack and release is set to extremely small values, distortions might occur due to the rapid increase and decrease in amplitude. A compressor's role is to attenuate a signal whenever it rises above a certain level. Again, as with noise gates, the point at which a compressor takes effect is the threshold. The degree by which the original signal is attenuated is called ratio. For example, if the ratio is set to 3.5 to 1, the original signal will have to increase by 3.5 dB in order for the outputted signal to have a 1 dB raise in amplitude. Compressors often have a peak or RMS setting. In simple words, if peak is selected, the compressor detects and responds to peaks, while RMS, which stands for root mean square, analyzes and uses the average magnitude of spaced samples. If we are working on percussive material, we might want to use the peak setting to compress a snare, for example. On the other hand, the RMS setting is more ideal using on vocals. Attack and release controls are also available to control timings after the compressor starts to take effect. An interesting setting found in compressors is the knee, which controls whether the signal is compressed immediately or more gradually at levels close to the threshold. Typically, compressors will offer a gain control, sometimes an input and output gain, to compensate for drops in overall level. A multi-compressor uses a number of compressors assigned to specific frequency bands. Delays can be complicated and tricky to use, so let's start from the simplest function of a delay effect. Delay effects store the input signal and hold it for a short time before sending it to the output. Most delays also feed a percentage of the delayed signal back to the input, making the signal reoccur several times, with each subsequent repeat a little quieter than the previous one. While mixing, you will probably come across different types of delay plugins or hardware units. Some of them might be referred to as sample, stereo, or tape delays based on their characteristics and available controls. What is important to understand in delays is their use in mixing. For example, they can be used for doubling individual sounds, making a recording sound as if more than one performers were playing the same part. Another use is for creating echo effects or for enhancing the stereo position of a track in a mix. The most common controls of delays are time, repeat, tempo, and groove, which control the effect's timings, such as the duration it takes before the first repetition occurs and how many times it is repeated. Many delay plugins will feature a sync option that automatically tries to adjust the previously mentioned parameters on the tempo of the given material. Delays are often synchronized to the given material in order to emphasize and enhance certain parts of a mix and simply to keep the effect more tidy. One of the most important controls of a delay effect is feedback, which controls how much of the outputted signal is sent back to the effect's input in order to reoccur several times before gradually dropping in an inaudible level. Wet and dry settings are used to adjust the amount of original and processed signal. More advanced delays can feature various filters that shape the tonal characteristics of the repeated samples. Let us make one thing clear right from the beginning. Reverb exists everywhere, in other words, in all acoustic environments. All of us are familiar with reverberation, even if we do not notice it in our everyday life. In short, reverb is sounds bouncing on the various surfaces of any space, in other words, reflections gradually dying out until they become inaudible. The same as delays, reverbs can be very complex and advanced tools. In relation to time, reverb follows certain stages referred to as the reflection pattern. In short, reverb effects are used in mixing to make our recordings sound as if they were captured in nice-sounding spaces, adding depth and character to our mix. There are various types of hardware and plug-in reverb effects based on where they originated from. Some examples are plate and spring reverbs, or a relatively newer type, convolution reverbs, which use impulse responses from actual spaces. The most common controls found in a reverb effect are pre-delay, which is used to adjust early reflections. More specifically, it determines the amount of time between the start of the original signal and the arrival of the early reflections. Room size defines the dimensions of the simulated room. Reverb time, as the name implies, controls the time it takes the reverb level to drop by 60 dB. Dry and wet or mix controls can be used to adjust how much of the original and processed signal is outputted. A high cut setting adjusts the point at which high frequencies are filtered from the reverb tail.